All right, we've been going over different differentiation rules. So we've been developing and proving all these different sort of shortcuts. And we've pretty much come to the end of that process. We've just established the chain rule. So now, what I want to show you is something a little bit different. So let's go back to sort of fundamentals. We've been working with functions a lot, right? Like talking about different types of functions and how to differentiate types of functions and differentiate different ways of functions combined together, like products and quotients and compositions. But what if you just have an equation? Not really a function, but just an equation. This equation might still describe like some shape, okay? Like in this case, the equation xy equals 1 does describe this hyperbola. And this hyperbola, if you pick a point on this hyperbola, it has a tangent line. It's a smooth, continuous curve, okay, except for this one infinite discontinuity. But it should have a tangent line. So we should be able to say that the slope of that tangent line is the rate of change in y with respect to x. But if we're not given a function, if instead we're just given an equation, how do you find that dy over dx, that rate of change? Well, one possible approach to this is to solve for y. So here, if you divide both sides by x, we get y equals 1 over x, which is like x to the negative 1, right? And then, if you've solved it for y, you can say, well, that means that I have a function, right? This is called the implicit form. This is called the explicit form, or function form. And then you can take a derivative of that to get your dy over dx is negative 1 over x squared. We've done that before for this particular function. So that's fine. But it turns out that you can also take a derivative and figure out the rate of change in y with respect to x starting from the implicit form. And that is called implicit differentiation. So how does that work? Starts like this. You take your implicit form, xy equals 1. I'm just going to do it for this example, and then we'll do it for other examples as well. Start with that. And then you take the derivative with respect to x on both sides of the equation. So derivative with respect to x of the left side equals derivative with respect to x of the right side. If the equation's values were equal, if these values are equal, their derivatives are going to be equal as well. So this is a valid step. Then we start applying differentiation rules. But as we do this, always remember that implied is that y is a function of x. It's not explicitly stated, right? And we haven't solved for y, so we don't have an explicit formula for like what y is as a function of x. But we want to think about y as if it depends on x. So in other words, y depends on x. It's a function of x because we want to know how the y is changing with respect to x. And if we want to know that, we have to be able to think. We have to be thinking about y as like being dependent on x, determined by it. So we're just going to keep that in mind as like a concept as we work through this. So the derivative on the left, we need to do a derivative of this product in this particular example. So we're going to apply the product rule right there. We're going to do the derivative with respect to x of the first function, which is just x, and then times the second function, plus the first function by itself, times the derivative with respect to x of the second function, which is y. So on the left side, we use the product rule, and it looks like this. Okay, it's u prime v plus u v prime, or f prime g plus f g prime, whatever you want to call it. On the right side, the derivative of 1 is 0, so that's easy. Now, what's going on over here? This derivative of x with respect to x is 1. So that's just equal to 1, so we just have y as our first term. This derivative, the derivative with respect to x of y, that's the literal thing we're looking for, right? That's what we're trying to figure out. So that, we don't have a name for it. Like, we can't really do that yet. We can't like calculate or do anything with that. Just call it what it is. dy over dx. Okay, but now that we have an equation that involves that thing we're looking for, we can solve for that. So subtract the y from both sides, divide by x, and you get dy over dx is going to be negative y over x. Okay, that's fine, but that doesn't look at all like what we got by doing it the explicit way, right? Okay, this is in terms, currently this is in terms of both x and y. Okay, that's usually okay when you're doing this type of differentiation. But if possible, it is nice to like eliminate the y by replacing it with some function of x. So generally the only way to do that is if you either started with an explicit format or if you get it into an explicit format. So if we go in here and we actually replace the y with 1 over x, you actually, a little bit of algebra there, 1 over x divided by x again does actually give us 1 over x squared, which is the same as what we would have had here. But you do need to go that extra step and put it in explicit format in order to eliminate what the y is, like eliminate the y variable from your answer. Often, with implicit differentiation, it's okay to have both x and y in your answer. There's just a few situations where it's convenient to go a little further and eliminate the y.